Johannes Schachenmayer on modified transport properties of dark eigenstates under strong light matter coupling.
Hello everyone, good evening, morning, good afternoon. I'm very sorry for crashing this exciting question session, but I hope I can make up for it with my talk. So let me share my screen. Yep. All right, so again, first of all, I would like to really thank the organizers for having me here presenting some of the work, and in particular, I want to talk about some of the research lines that we've been really very interested in the quantum antibody theory group here at the university in Strasbourg. So the title says today I want to talk about modified transport property of dark eigenstates under strong light matter coupling. So let me start by a motivation, and as quite often the motivation here is really an experimental one. And this is because in Strasbourg, since about 10 years, there have been a very exciting series of experiments in a group of Thomas Edison. And what they basically do is that they study how they can change material or chemical properties by using strong coupling to cavity modes or to other non-local modes, such as, for example, in this experiment here, which has been the main motivation for the work I want to talk about today. So let me just briefly say what they did in this experiment. So what they did is they put an organic semiconductor, so a bunch of organic molecules, and they engineered a situation where an electronic transition in these molecules strongly couples to a delocalized surface plasma mode. So you can think about it, if you like, also a bosonic mode, just like a photon, which is all over the place. And then what they find is whenever they engineer here a situation where one gets a strong coupling regime, meaning that these organic molecules can exchange energy with the surface plasma much more quicker that they can dissipate it, then of course one has to describe the system as a hybridized system with some new type of polariton states. And whenever they have had this situation, they found that they can boost the conductivity of this organic semiconductor by orders of magnitude. Here seen, for example, as these boosted IV curve lines. And I really want to emphasize that this is not an isolated experiment, but there have been a series of experiments where they show with such strong coupling scenarios, one can really modify also, for example, chemical reactivity of molecules, or even indications now that you can change temperatures of superconductors and so on. So this is a very exciting topic, especially for us theorists, because a lot of these effects, they're really not understood. And this is exactly what we are trying to do. So our motivation is really what we try to do is, because we are physicists, we try to really construct some minimal quantum optics model, then to basically explain some of the effects behind those experiments. So today I want to not talk about charge transport, but I want to talk about a simpler problem of just energy transport. So, and I want to talk about energy transport really in the simplest possible scenario I can think about. So consider that you have a bunch of two-level systems and you have a single excitation. And then, for example, there are some dipole-dipole interactions. So this excitation can hop from one side to the other one. And every time it hops from one to the next side, it transports an energy of this level spacing from one to the next side. So this is energy transport. Now, of course, if you go to a more realistic scenario, you should add some disorder or some imperfections. So, for example, one can look at some diagonal disorders, so some random offset in these two-level systems, or some off-diagonal disorders, some noise in this hopping constant, or also some open system noise, such as spontaneous emission or dephasing, etc. So one way to study transport in this scenario is that one, for example, now considers a scenario where I have this chain, and let's assume that on one side of the chain, I couple my system to a hot reservoir, and the other side of the chain, I couple it to a cold reservoir. And then what I can do, I can write down a master equation for this and compute a steady state current. And then if one has this type of imperfections, what one typically finds is that a function of the length of the system here, this current is going to decay exponentially, here seen by this logarithmic scale. And so today, I really only want to focus about diagonal disorder, because that's already enough to explain this exponential decrease of the current in the system. And this is, of course, extremely well understood. This just is a consequence of the well-known Anderson localization, which has been limiting transport since 1958. And so the model that I want to look at now is just really a situation where I have this simple excitation, which can hop in the chain. And then on top of this, on each side, I have some diagonal disorder, meaning that on each side, I have some random energy offset, which here I uniformly take from an interval of minus W over 2 plus W over 2. So with W, also called the disorder strength W. And then, of course, it's extremely well known that if this disorder is strong enough, then in 3D, then the eigenstates of the system are localized, meaning that they are not extended Bloch functions anymore, but now they are localized on individual sites, and they have these tails which decay exponentially around a particular site, so you have this localization length. And then in 3D, one can describe this as a transition between extended states and localized states. Okay. And of course, this localization leads to this exponential suppression because it relies on this overlap between these very small tails. So now the first question is, can like a cavity coupling overcome this? And of course it can. This is quite trivial to see. So the model that we wanted to look at now is we take this disorder model and then we simply add an additional homogeneous coupling of these emitters to a cavity mode. So each emitter can emit a cavity photon and can be coherently reabsorbed by all the other ones. So that we end up with this Travis-Cummings type Hamiltonian where each emitter couples to the same photon mode. So this is an collective coupling, and this is important because one gets sort of this collective enhancement of the coupling strengths, if you like. One way to see this is one can go simply to a quasi-momentum picture. So I do a Fourier transform of these sigma matrices to quasi-momentum modes. And then I see that this last term only couples to the symmetric Q0 mode, also called the bright mode. And the important thing is because, of course, of this normalization of this Q0 mode, this coupling to this mode just increases collectively with the square root of the number of emitters, which means I can easily achieve such a so-called collective strong coupling regime where chi square root of n is much larger than the hopping and the disorder in the system. Now, if I am in this collective strong coupling regime, then I have only this last Hamiltonian term that plays a role. And then I have two important eigenstates in my system, which are called the upper and the lower polarity modes, which are really just the symmetric and the antisymmetric superposition of having a photoexcitation and having an excitation in the symmetric mode, which is distributed all over the system. Now, of course, what happens if I have this order, then I have my usually localized eigenstates here, but then I also have these two polariton states, which have this extended density throughout the system, as seen here in this simple numerical calculation. So, of course, these polariton modes I can use to enhance my transport in the system. And this is something which is well known. We studied this, for example, already in 2015. So I can do exactly the same type of setup. Now my cavity coupled disordered emitters, I couple them to a hot and a cold reservoir, I compute steady states. And then I see that without the cavity, I get an exponential decrease of the current, here seen on the log-log scale. But then it turns out if I go to this collective strong coupling regime, I find in a regime where this current only decays algebraically as 1 over n squared is the distance. And this is quite easy to understand if one thinks about it a little bit. It just simply comes from the fact that this extended state, this polariton modes, this bright mode has sort of an amplitude of 1 over square root of n on the first side and on the last side. So if I want to couple an excitation into this polariton and out of it, I need a 1 over n probability and a 1 over n probability that gives rise to this 1 over n squared term. Okay, so all of this is nothing super exciting and nothing new, but the question what we wanted to recently now look at, so what about the dark states in the system? Because of course I don't have only this Q0 mode, but I also have this other finite momentum mode. And now, of course, if I don't have any disorder term in my system, then of course there is these dark states, they're completely decoupled. And if I'm interested in the physics only from the hopping and the Q0 mode, then I don't need these dark states. But what happens because of this disorder, which is localized in real space, of course, this disorder couples these modes in quasi-momentum space. So if I have this order in the system, then these dark states should become important. So the motivation of the work that I really presenting today was now, so how do these dark states contribute to this modified transport? Or in a more bigger picture, really what happens to the phenomena of Anderson localization in a cavity? Okay, and so before I start, I just want to introduce a few quantities. I will show plots on the next slides. So I first want to introduce something calling the transport probability. And this is simply a quantity when I say, imagine I have my chain and I start on a particular site, let's call it the source site C. And then I ask, what's the probability at another site N? And of course, this is a time-dependent quantity that's going to fluctuate. To make it time-independent, let's say we're interested in the infinite time average of this quantity. And then if one computes this, it's a very simple calculation. You will see that quite intuitively, this transfer probability is simply the probability to go from the site C into an eigenstate, and then to go out of this eigenstate on site N. And then I have to sum up all of the eigenstates. Another quantity I'm going to look at is the so-called return probability. It's now trivial to introduce. It's just n equals c, so it's just really the infinite time average probability to remain on a particular site. And finally, I want to introduce this inverse participation ratio that I'm sure many of you are aware of. So you can think about this just for each eigenstate. You can define a number that tells you how extended or localized an eigenstate is. So for example, if you have a fully localized eigenstate, then you have in this sum here, you have all terms of 0 except one is going to be 1. And then this IPR of this eigenstate is going to be 1 and it's going to be independent on the system size. However, if I have an extended state, then really each of these weights is going to go as 1 over n squared, and I have n of those terms. In that case, I get now a small number that decays with the number of emitters I have as 1 over n. And that's just the IPR. And just maybe a side remark, of course, it's also quite nice to remark that this IPR, you can think about it as really, it's kind of a system average return probability for a single eigenstate. So if I sum up all of the IPRs of all the eigenstates, I get the average return probability for all the different sites in the system. Okay, so let's now see what happens here if you turn on this cavity coupling, this collective cavity coupling here defined as GC. And here in this plot, I simply show you what happens to the probability to remain on the same site for different GCs. And I show this here on this plot as a function of the disorder strength. So I go more disordered here from the left to the right. And so you see, for example, if you're in this fully delocalized regime where this disorder is completely negligible, just focus on the GC equals 0 line for now, then you see that this return probability, of course, is very small. It's almost 0. It goes to 0. So in this case, it's really not localized. On the other hand, if I go to the limit where I have very large disorder, I see that I go to a return probability of 1. So in this case, I put my excitation somewhere. It's going to stay there in the infinite time average. And now something interesting happens if I turn on this cavity coupling. So first of all, of course, everything gets more extended, if you like, because the return probability decreases. But then, interestingly, in this strong coupling regime, we saw this plateau coming up here, which is more or less at a value of 0.4. The same interesting thing happens if you now look state resolved is the IPR, if you like. So here again, just a reminder, I define my IPR really only for the dark states. So I forget about the polariton states now because I'm not interested in them. And we find here normalized energy range between 0 and 1, which encompasses all these dark states. And then you see on the left side, you see the picture without the cavity. This is the usual result you get for Anderson localization. Actually, this vertical line here just gives you the point of the Anderson transition. And then you see on the left of this, the IPR is going to scale to 0 for large n, whereas on the right of this, it's going to be a constant, and for large disorder, it's going to go to 1. Now, on the right side, you see how this looks like for the cavity scenario. And now, interestingly, now you have again this extended area and you have this fully localized area. But then we really saw this emergence of this large area where this IPR for each of these eigenstates remains somewhere like at around 0.4. And in particular, in the middle here at like 0.5, this is exactly where the photon energy sits. They are also really this IPR states, they really extend to very large disorder strengths. So that's kind of interesting. And lastly, let me show you how these states actually contribute to transport. So here now on this last plot, I show you this transport probability over a large distance. And I also resolve it here for different states. So this is the plot really for a particular fixed cavity coupling strength and a disorder, and then I increase just the number of emitters in the system. So what you see here is that at one point after a certain number of emitters, one reaches the strong coupling regime, and then these two polariton states start to pop up, which show this typical 1 over n squared behavior of this transport probability. And then quite interestingly, if I look at the dark states, they actually they contribute better to transport in terms of a 1 over n scaling. And one can easily understand this because I just showed you before that we have this large area of an IPR, which is constant and does not scale with the system, which means that the return probability is constant and does not scale with the system size. But then it means that there's a certain fixed probability to not stay on the site. And this probability spreads out of all the other n sites. And this gives rise to this 1 over n decay. Okay, two remarks about this plot. This looks a bit like the dark states would be just much better for transport in the polaritons. But of course, one thing you see here, this is a disorder average plot. And you see that the dark states typically have very large fluctuations, whereas these polaritons, they're kind of like very smooth. I will come to this exactly on the next slide. And then I also just quickly want to remark is, of course, This is like our definition of a transport probability, but one can also look at other type of transport quantifiers, and then one can see kind of like different scalings. Okay, but now let me explain what is actually really going on and where this IPR scaling and this transport probability comes from. And so let me give you the intuition, and I think the intuition one can best understand if one just looks at a simplified model where for now completely neglect about the hopping in the system. So let's say that we don't have any hopping and we only have the disorder and we only have this cavity coupling. Well, if I put the cavity coupling to 0, then of course all the eigenstates of my system, they're going to be completely trivial, because of course they're just going to be fully localized states on all the sides or being localized in the cavity. But now if you go to this collective strong coupling regime, what actually happens is that you have these two polariton states. But if you have two polariton states, it really means that there are only n-1 dark states left over. And what happens now is that these states, they want to localize, but they have to localize on n sides. So what you actually see, if you look at the eigenstates, how they look like, they are typically very localized, very sharply peaked, but not on one side, but on two or more sides. And the way one can understand this is that essentially now these new eigenstates, they're going to have a weight on two states, which are very close to each other in energy space, but in real space, they can be very far from each other. And this is why they basically have localization properties in terms of the IPR, not the value of 1, but of 0.4, because they localize on more than one side. And we call these states semi-localized states. Okay, I think I'm already pretty much up with my time. I just want to very quickly also mention that quite interesting is also to look at the level statistics of these new semi-localized states, because just as a quick reminder, one can also define sort of the energy difference between neighboring energy levels of states. And then this is also the statistics of these energy spacings one can use to identify localized and extended regimes. For example, if I have a situation where this order dominates my analysis model, then I simply see that all of these levels are random and I get a Poissonian statistics. Whereas when the hopping is important, I have some off-diagonal terms. What happens then is this off-diagonal term leads to some repulsion of the levels. And then I get, instead of this Poissonian statistics for the spacings, I get this so-called Wigner-Dyson statistics. And one can check this, one can really see this in a simple simulation here. There's no cavity. It's just in this localized regime, one finds a Poissonian distribution of the spacings, whereas here in this extended regime, one finds this level repulsion at short distances, and then this Wigner-Dyson shape. And the question was now simply for our cavity semi-localized states, what do we find there? And quite remarkably, we find neither the one nor the other, but in fact, what one finds this so-called semi-Poissonian statistics, which also shows some type of level repulsion. But then it differs from the Wigner-Dyson statistics in the sense that in the tails it decays as e to the minus 2s instead of e to the minus s squared. Okay, and this is something one can also understand analytically. Okay, so from now I just want a little bit of an advertisement here. I just said analytically one can understand all of these things really if one goes to the j=0 limit. So if one neglects the hopping, because then actually, this model that we're looking at, it's equivalent to the so-called central site model. And if you look at the Hamiltonian matrix of this model, it has the shape of an arrowhead. And turns out that there is so what we're dealing with now is the disorder we deal with random arrowhead matrices, and one can relatively easy find analytical estimates for this also in the infinite n limit for this. And these all confirm all of these things in terms of the IPR, the scaling of the IPR, and the level statistics that I was showing you in the plots before. Okay, but with this, I'm at the end. So just to come to the conclusions, I think they are very surprising and exciting new experiments that really demonstrate that you can use the cavity to enhance material. And important is this is sort of, people also call this vacuum enhanced, because the cavity is not driven. So this is not photochemistry or photophysics, but the cavity is in the dark. And just because of the strong coupling, you can change the material or you can change the chemistry. And theories for this are really needed at the moment. So what we really do is that we construct minimal models using like the minimal degrees of freedom, like electronic photonic degrees of freedom. And then we try to understand some of these effects. And so here, for example, in this paper, we studied sort of the fate of Anderson localization in a cavity. And the most important result is that we find sort of this new type of states, which we call semi-localized, which have properties like normal localized states in the sense that they have an IPR that does not scale with the system size, but it's not going to 1, but it stays constant at a value of like 0.4. And the level statistics of these states is semi-Poissonian. That's why we call them semi-localized. And in general, one should really keep in mind that these dark states in the presence of disorder, they are apparently very important to understand cavity modified stuff. Okay, yeah, just one little outlook at just a bit of advertise. We did a lot of work just with this type of models that I was talking about now, where we consider only electronic and photonic degrees of freedom. Now, very exciting, I'll just advertise this work. I think it's very interesting to now go to models where you also keep, for example, molecular vibrations in the picture. So you also have nuclear degrees of freedom, because that's really needed if you want to understand sort of cavity modified chemistry. And we did some first steps in this direction now. And with this, let me just flash a picture of the team in Strasbourg, and thank you for your attention.
Great. No more last slides?
No more last slides, just the last slide.
Thank you very much. There's one hand up already. I just wanted to ask about the experimental motivation. I may be wrong, but I was under the impression that it's not many experimental systems where one can actually test for Anderson localization. So is it known that these organic semiconductors actually show Anderson localization, or is it rather that you now show it through these experiments?
No, it's not. So in these, especially the organic systems, they're so messy. And I think the most important ingredient is all the vibrational degrees of freedom that you get in this. So if I think about the vibrational degrees of freedom, and I think about each of my emitters essentially coupling to an harmonic oscillator path, then I would get some dephasing in this. And I think that dephasing is the thing that dominates everything. And in these systems, it's clearly not possible to just really make a statement about Anderson localization being the coherent mechanism that inhibits transport. So
it's more the modification of randomness somehow.
Yes. And yeah. I mean, in our paper, we propose to possibly use some cold atom systems in a cavity to really see this, because they're of course much cleaner. And of course, cold atoms have been very successful in demonstrating Anderson localization. But in this organic semiconductors not. But it's really, the theory is not so much to really explain this one experiment. It's sort of to see what are the mechanisms behind.
Okay, great. Thanks very much. Chris, you had your hand up, went down again. So maybe then I can ask.
I was clapping.
Ah, sorry, I just peripheral vision. Okay, thanks. Maybe then I can ask one more question. So then the chemistry, the chemical properties, you mentioned them in the end again. So that's not really a transport property, right? So is that more of a density of states thing then, that you simply change the states in the system and thereby change all properties? Or how should one think about that?
Well, not always. There's also things like electron transfer reactions.
Sure. Yeah.
It's then really about sort of the charge transfer of the one electron. But so what we're doing right now, I mean, of course, if you talk about chemistry, you should look at really potential energy surfaces and then look at the nuclear dynamics of nuclear wave packets on these potential energy surfaces. So what we're doing right now is essentially we look just at sort of toy model molecules which just have one vibrational mode. So we have an harmonic oscillator, and you have sort of a potential energy surface, which is different from like the ground state, the electronic ground state, and the excited state. Right, so you have a displaced energy surface, and this gives rise to the vibrational coupling of the electronic states to the motional states. This normal Holstein coupling, if you like. And then what we do is we do an harmonic approximation at the moment to have sort of a spin boson model where we have a coupled harmonic oscillator coupled to the electronic degrees of freedom, and then in addition the cavity coupling and the disorder. And then we look at, now we are interested in just the vibrational dynamics, how it changes because of the presence of the cavity.
Right. Okay, thanks. There's a question by Jean-Philippe.
Hey, Johannes, it seems that at least for the last part where the J was small or zero, it sounds like you're describing homogeneous broadening. From a purely optics point of view, you know, it's very common actually in most experiments where you have disorder to have this kind of distribution of different levels that couple to one mode. And I'm wondering, if you look back in sort of very old experiments on quantum optics, sort of before one could, for example, freeze the motion of atoms, is there anything you could reinterpret with your model?
Well, in that sense, I mean, I think you're mostly referring to if it would do some spectroscopic experiment.
Yes.
Right. So I could, and I mean, people have done this also here. I mean, you see, for example, if you compute like spectra of these systems, I mean, you see always the the lower polarity mode and the upper polarity mode, and of course, you also see the dark states in the middle. One can do this. So in that sense, yes, they see it. But I mean, of course, the question now here is really a new question, because the question is now, like within those dark state manifolds, like if you create a localized excitation, right? So you probe your system differently. It's not like a spectroscopic probe of your state, but now you put some excitation at one spatial point in your system, and you want to see how efficiently it goes away from this. Right? So it's just a different way of probing the system, but I agree that that you see the same type of states and you just populate them with the spectroscopic experiments if you are, if you tune it correctly.
Thanks.
All right, thank you. Any more questions? That is not the case. Then I would say let's thank Johannes again.